This is section 5.2, the definite integral, and our first objective is to rewrite a Riemann sum as a definite integral and vice versa. When we're done, I'd like you to be able to discuss which of the examples in this objective was the most difficult and write 2 tips that will help you remember how to do these types of problems in the future. First, I'd like to revisit the RAM concept from section 5.1. Only this time, let's allow f of x to cross the x-axis and have some negative outputs. When we create a partition for a general function on the interval from a to b, we slice the interval into n equally spaced subintervals. Let's let the width of each subinterval be that same delta x we've been using all along. Notice that this delta x is still the width of each rectangle, only now the rectangle can either be above the x-axis or below it. Notice, too, that we are no longer being systematic in our choice of input. In other words, we don't always use the same type of x value with every subinterval. Instead, we select randomized x sub I asterisk in each ith interval, and then we use the output f of x sub I asterisk to write a new sum called a Riemann sum. Here we can see we've taken that general function f of x. Part of it was underneath the x-axis and part of it was above the x-axis. We split into n subintervals, and then within each subinterval we chose a random x value and then created a rectangle height. And in this case, some of the heights are coming from negative values. So this Riemann sum is a sum of the form, here's that Greek sigma that means add everything up, all the terms, that is the outputs associated with those selected x's times the width of the subinterval. In this case, f is a continuous function on the closed interval from a to b. That x sub I asterisk is some point in, and the delta x is the width of this ith subinterval in some partition of the interval from a to b. If we think graphically, we can see that any Riemann sum will actually be an estimate of the accumulation of the function. We have to be careful to recognize that the accumulation can be different from the area between the x-axis and the function, since area can never be negative, but accumulations can have values less than 0. For example, if we look at this accumulation until this x-intercept, what gets accumulated under f is going to be a negative value, whereas this accumulation, which is above the x value, will represent a positive accumulation. To help this make sense, let's consider this function graphed below, which shows the profit in dollars per day that a certain store earns over the course of a month. We did problems like this in section 5.1 where we had the rate, and notice this is measured in dollars per day. And then the input, or the x, is representing the days of the month. So we have this 31-day month, and we have the rate at which we are accumulating money. So this accumulation that is above the x-axis is going to represent profit. It will be a positive value, whereas this accumulation down here will be loss. The store is losing money on those days. Again, we have some profit. So if we are to accumulate from A all the way to B, or over the course of the entire month, we'll see that we will eventually come out ahead. We'll lose some money in this downtime, but the rest of the time we'll have a greater area above the x-axis than we do below. So we'll come out ahead, but in the accumulation, this will be represented by a negative number. So far, we've only been working with estimates of a function's accumulation. But what happens as n gets larger and larger? Or what if we allow n to approach infinity? When we do that, we get what is called a definite integral. So a definite integral, we will let f be a continuous function defined on a closed interval from a to b. We'll divide that interval from a to b into n subintervals that have that delta x as the width. Then we will choose x values in each of those subintervals, and we will let these asterisks be the sample points on the subintervals. So this x sub I asterisk will be in the ith subinterval. Then this definite integral, which is the new vocabulary of f from a to b, will be represented with this capital I, and it will be the limit as n goes to infinity of that sum. And here's the y coordinates times the width of each subinterval. It turns out that as long as f is continuous, this limit is always going to exist regardless of the partition, and f will be called integrable. So remember, we had differentiable was the adjective we would assign to a function that had a derivative at every point. Well, here's one where we say that the function is integrable when the definite integral exists, when this number is a finite value. Furthermore, even if f is not continuous, but its discontinuities are countable and bounded, f is still going to be integrable. So this function here is integrable because its discontinuities are bounded and you can count them. And this one is not integrable because its discontinuity at 0 is unbounded. So one of the ways I like to help kids think about whether something is integrable or not is if you can cut out a piece of carpet and cover up the entire graph from the region from A to B, then you'll end up with an integrable function. So I could cut out a piece of carpet or a piece of paper and I could completely cover this picture. I couldn't do that with this one because this asymptote is going to take it up and up and up forever. So I would never be able to get a piece of paper or a piece of carpet large enough to completely cover this. So this one's not integrable and this one is. Now Leibniz, the same mathematician who gave us the notation dy dx for derivatives, he thought the notation for a definite integral was a little clunky. So he created a new notation that was eventually adopted as the standard. This limit as n approaches infinity of the sum from I equals 1 to n of f of x of I asterisk delta x on any partition of A to B, he thought this, it took a lot of space to write, it was hard, had extra information that we didn't want to waste writing this on any partition. So he condensed this into this notation right here. And this is called integral notation. In the integral notation, this elongated thing right here is actually a capital S for sum that has been stretched out. So we have the sum of y coordinates times widths. Now let's think about what happens to this width as n gets bigger and bigger and bigger. If we had a partition from A to B and we cut it into 2 and then we cut it into 4 and then we cut it into 8 and then 16 and we keep getting finer and finer and finer and finer, that delta x, when we have an infinite number of these little subintervals, that delta x is going to go to 0. And it's kind of going to hopefully remind you of when we had a curve and we were moving from one to the other on these points and creating a slope. So if this was x and this one was x plus h and we let h move to 0, then we ended up getting that instantaneous slope that had an infinitesimally small distance for its run. Same thing here. That delta x is going to get tinier and tinier and tinier. That distance between the two will get so small that it will be immeasurably little, and we'll change it to a dx. The other thing that we have in here are the upper and lower limits here. So this a to b is the interval that we are doing this sum over. So we can translate this information and put it onto our integral symbol, and it tells us what our left bound is and what our upper bound is. Then, because we are going to be hitting every single x value in the entire interval from A to B, we no longer have to talk about the selections because we're going to choose all of them. So we will replace this x sub I asterisk with just a plain x. Now the vocabulary that goes with this is we say that this thing inside, this f of x, is called the integrand. This is the integration symbol, and these are our upper and lower limits of integration. Now this letter x turns out to be a dummy variable. It doesn't matter what variable you have. I could have an f of t with respect to t. I could have an f of p with respect to p, and all that's telling us is that graphically, if we have some function and we make it depend on t, and then this is my f of t, and I'm going to accumulate from A to B, well, that accumulation is going to be the same whether this is an x and an f of x, or an R and an F of R or a P or whatever we want to make it. It doesn't matter because the picture does not change, nor does the accumulation. So that dummy variable becomes interchangeable. You can put whatever you want in as long as those two match. So let's look at this first example where we find the value of the integral given the graph. Now on this graph I have told you what the exact accumulation is. So from -6 to -2 that accumulation was 15. That's representing that area because the area is a positive number and the accumulation is a positive number. So if I want to talk about the accumulation from -6 to -2 of the function, I would get simply 15. With the next one, I want to go from -6 all the way to 4. So I'm going to accumulate from -6 to -2, and then I will continue accumulating all the way to 4. Now notice in this case that the 18 is underneath the x-axis. So the area of this section is 18, but because it's under the x-axis, we have to treat the accumulation as a negative number. So the accumulation going from -6 all the way to 4 will be 15 minus 18, which is -3. If we want to start at -2 and go to 7, then we will accumulate the -18 first and then the 4. So we'll end up with a -14 as the accumulation. Lastly, if we accumulate from -6 all the way to 10, we'll have positive 15 minus 18 plus 4 minus 7. So we're at -3 plus 4 is a 1, minus 7 is a -6. With example 2, we're going to start getting at the objective, which is we want to go back and forth between the Riemann sum notation and the definite integral notation. And we can see here that we're starting with the definite integral notation, and we're going to convert this to an approximate Riemann sum using a delta x of 1/75. Now, one thing you should know is that these Riemann sums are always going to be right. That just tends to be the convention. Every problem I've ever seen that's like this uses a right Riemann sum. I'm not sure why, they just do. So we're going to work with the convention so that you're able to get all the correct answers. If we think graphically about this, it tells us I want to accumulate from 0 to 3 on this function 1 over 1 plus x. So this is a rational function with an asymptote at -1. So you can see that I've created this over here, and then we are going to accumulate from 0 until 3. This area, since it's above the x-axis, will be the same as the accumulation, and we want to approximate that accumulation using a delta x of 1/75. So what that means is that from 0 to 1, I'm going to get 75 rectangles. So I'm not going to be drawing this to scale. I'm just going to draw a couple of sample ones so that we can kind of get the hang of it. And we can see here that I'm going to do a right-hand sum. So this first edge here, this first right edge that I'm going to plug into the function to get the height, or the y value, is going to be 0 plus 1 of those delta x's. So we can say that this integral is approximately the width of each rectangle times the function outputs for each rectangle. So on this one, since the rectangle is above the x-axis, we're going to have f of my a plus 1 of those delta x's. If I want the next one, it will be the width times f of a plus 2 of those delta x's. If I continue, I'll get f of 3 of those delta x's. And then I've done 3, so I can do a ... to intimate that it's continuing until I get to my final one. So I need to know how many 75th steps. So a step is 1/75. How many of those do I need to get all the way out to 3? Well, I get 75 here, 75 here, and another 75 here. So that will be 225 of those 75ths. Now this is the generic accumulation with the f's. What you'll find is that in your homework, they will have this actually plugged into the function. So if I plug 0 plus 1/75 into this function, I will get a 1 over a 1 plus a 75th. My next one will give me a 1 over a 1 plus a 2/75. My next one will give me a 1 over a 1 plus a 3/75. And I can continue on until my final, which will be 1 over a 1 plus 225/75. If we look at part B now, we can see that I've graphed a 1 over x, which is yet another rational function, only this time the asymptote is at 0, and I want to accumulate from 1 to 4. Again, that delta x is a 1/75, which means I'm going to be slicing this region into widths that are 1/75 across. My first right edge, a little crooked here, will occur at 1 plus 1/75. So that means this approximation will be 1 over the 75, which is the width of the rectangle, times f of my a, which is 1, plus 1/75. For my next one, it will be my a plus 2 of those 75ths that gets plugged into f. For my next one, it will be f with 3 of those 75ths added to 1 plugged in. And I continue the pattern, and I'll get all the way out to my last one, and my last edge is going to be the a plus 225 of those 75ths. If I now plug these into my function, you will see that I'll get 1 over whatever's inside. And I will continue that process. I'll plug 1 plus 3/75 into the function 1 over x, and I'll plug 1 plus 225/75 into the function 1 over x. Now hopefully you have noticed that this approximation was the same as this approximation, and yet the definite integrals looked different. So what this is illustrating is that just like you can have summation notations that are different for the same sum, you can have definite integrals that are different for the exact same sum. And if you think about what this is representing graphically, this was representing this red area here, whereas this one was representing the blue area. And if you notice, I can move this blue area and it will match up exactly with the red. We're measuring the same thing, it's just we've shifted the graph to the left 1 unit. With our third one here, part C, we can see that we have this graph that is y equals x squared, and then we are accumulating from 0 to 1. So we are going to approximate this area by using rectangles whose widths are 1 over 100. So we'll get 100 of those rectangles in here. And we're going to use the right sum like we have before. So this will be approximately the width, which is 100, times the function evaluated at 0 plus 100th, plus the function evaluated at 0 plus 200ths, plus the function evaluated at 0 plus 300ths, and on until we get to the final, which is f of 0 plus how many steps of width 1 over 100 do I need to get all the way out to the final right edge of 1? Well, that is 100 of those hundredths. If I rewrite that now as function outputs, I will have 1 over 100 times that 0 plus a 100 squared, plus 2 100 squared, plus 3 100 squared, and on to my final one. Most of the time you'll find that when a is 0, they cease to write it. So this one would not show up. They would just have it look like this. Now the reason I've written these out like this is that in example 3 we're going to be going backwards. And before we can go backwards, we have to think very carefully about what our options are for identifying the pattern. So in example 3, we're going to start with things that look like this, and I'm going to ask you to go back to the integral. So the first thing that we're going to identify that's pretty easy is that delta x. So I'm going to pick a different color here, and we're going to see that that delta x is always what's out in front. And we're going to notice that that delta x is what turns into the dx. So this 1 over 100 turns into the dx, this 1 over 75 turns into the dx, this 1 over 75 turns into the dx. The next thing we're going to look for is we're going to look for function inputs. And how we identify them is we look for inputs that differ from each other by a delta x. So I'm going to switch colors here, and I'm going to look for inputs of functions that are 1 delta x away from each other. So if I take this and I add 1 over 100, I get the next one. If I add 1 over 100 to this one, I get the next one. I just keep going down the pike until I have the last one. So we can see here that my input, now this is where it gets a little tricky, because when I wrote it out in the function notation, my input was the 1 plus 1 over 75. So that means I'd need a box around this whole thing. Notice if I add 1/75 to this input, I will get the next input. Similarly, add it again and add it 222 more times and I'll get to this one. Now with this one, my input was 0 plus 1/75 or 1/75. So I can see that this was the input this time. Now the reason it's important to box the inputs is because it enables you to figure out your function and your a and your b. So if I want to get to here, I need the dx. Remember that came from the delta x. I need to know my inputs and my function, and then the a and the b. So once we identify our function inputs, then it becomes much easier to identify the big overarching function. If I look at the whole term here, and I replace the input with an x, we see that the function becomes 1 over 1 plus x. So here's that function, 1 over 1 plus x. If we look here, and we box the entire term, and replace the input with an x, we again see that the function is 1 over x, which is what's showing up in the integral. Now the last thing we're going to have to figure out are the a's and the b's. The b, this number on top, is our last right edge. So it was our final input. 225 over 75 gives me the 3. Similarly here, the last box has a 4. So that means my upper limit is a 4. So let's apply that down here. We can see that the box turns into an x and the entire thing here becomes the function. So x squared is the integrand of the function. My upper limit, 100 over 100, so that means 100 over 100 becomes that 1. The last thing is these a's. How do I figure out the a? Well, if we think about our first subinterval, the very first one that we plugged in, it was a plus a delta x. That was the very first one that got plugged in. So we have to ask ourselves, what is this box minus the delta x? And if I do that, I see that I get a 0. This box here minus a delta x is going to give me the 1. And this box here minus the delta x gives me the 0. So let's see if we can now apply this pattern in example 3. If we look at example 3, identifying delta x, remember that is what's outside. So we have a 1 over 32 is my delta x. Next, we're going to look for inputs. We want things that differ from each other by 1 over 32. And we can see that that is these innards. If I identify my b now, it's the last input. So b will be 1. My a is the first input minus delta x. So my a is 0. Lastly, I need to identify my f of x. Well, the f of x comes from replacing the input box with the letter x and then looking at the entire term. So that entire term is going to be the cube root of an x. So now that I've got all the pieces, I can put it together in the integral. I will do the summation from 0 to 1 of the function times the dx instead of the delta x. Do it again. Here we can see that the delta x is that 1/50th out in front. So I'm going to look for inputs that are 1/50th away from each other. One way to do it is to choose the 1/50th, because if I add delta x, I get my next input. If I do that, I can see that my delta x is 1/50th. I can see that my a is this 1/50th minus delta x, which is 0. I can see that b is the last box, which is 2, and I can see that the function will be 1/2 plus x. Put that all together and create the definite integral 0 to 2 of 1/2 plus x with respect to x. Now, what if I chose not to box that particular thing? What if I wanted to box the entire denominator? That's a viable input because if I add 1/50th to this, I get the next input. And if I add 1/50th to that, I get the next input. If I continue adding until the end, I will get my final input. So in this case, I have delta x is still 1/50th. Only now my a is this entire thing minus 1/50th, which will give me 2. And b will be 2 plus 2, which is 4. And my function will now be replacing the input with an x, so that's a 1/x. Notice that graphically, I will be getting the same area. I have just shifted the graph 2 units from where it started. So let's try the next one. Next one's a little bit tricky. The reason it's tricky is that this delta x mandates what has to be chosen. The error that most kids make is they want to box the entire thing. But if I add 1 delta x, or 1/75th, to a pi over 75, I do not get 2 pi over 75. So my input is actually a 1/75th, followed by a 2/75th, followed by a 3/75th, all the way up to 375ths. So once I have that, I can write my delta x is 1/75th. I can write my a is 1/75th minus delta x, which is 0. My b will be my final input, which is 4. And my function will be the delta x, or excuse me, the input gets replaced with an x. So I'll have sine of pi times x. Put it all together and write it as an integral. We will accumulate from 0 to 4 on the function sine of pi x with respect to x. Notice with this example that my delta x is going to be a 1/n, and my input has to differ from the next input by a 1/n. We can see that a will be this input minus delta x. We can see that b is the final input, and we can see that the function is the input replaced with x. So this entire thing here becomes an x squared. Turns out this limit will be equal to the definite integral from 0 to 3 on x squared. With our final 2 examples, I'm hoping you're starting to get the hang of it. You can see that this 1/n is our delta x. We have a choice on our inputs, but for this piece, let's try the 2/n, the 1/n, the 3/n. Notice they differ from each other by 1 delta x. My a will be 1/n minus 1/n, which is 0. My b will be what's in the final box, which is 1. My function will be this entire first term with the input replaced with an x. So that would give me a 1/2 plus an x. Therefore, the integral will be the accumulation from 0 to 1 of 1/2 plus x with respect to x. Now remember, I could have chosen to box the entire denominator because if I add delta x to that, I will get the next box. So that's viable input. If we choose to box that way, then delta x will be 1/n, my a will be 2, my b will be 3, and my function will now just be a 1/x. So again, graphically, we are going to have the same accumulation in the same area. They're just shifted 2 units away from each other. Final example, again, we have a choice. We can select to box 1/n because these are 1 delta x away from each other. And if we choose that, we can see that delta x is 1/n. My a will be 1/n minus 1/n. My b will be what's in the final box. And my function will be replacing that box with an x. So the integral will be from 0 to 3 of my f of x dx. Now again, my other option was to box the entire sum here because these two differ from each other by a delta x. So in this case, I can let delta x be 1 over n. Can let a equal 4 plus 1 over n minus 1 over n is 4. B will be what's in this entire box, which is 7. And my function will be 3 over the sine of this entire box turns into an x. So in this case, we could also have an indefinite integral that represents this sum, only it would be written the integral from 4 to 7 of 3 over the sine of x with respect to x.